this series of slides is Shor's algorithm, one of the most exciting applications of quantum computing. Let's introduce RSA encryption. RSA encryption is what we depend on to secure information. It makes data appear completely random unless it's viewed by the intended recipient. For example, if we have a plain text message, it'll be combined with a function with some secret key in order to create ciphertext. If the encryption key factors are kept safe, data cannot be decrypted without significant time or compute resources. RSA encryption relies on the difficulty of factoring the product of two large prime numbers. Think about it. Whenever you multiply two prime numbers, that's relatively easy, but determining the prime factors is very challenging. The best classical methods for prime factorization involve this guess and check as a procedure. It's not very efficient. What if prime factorization is easier? Quantum factoring, Shor's algorithm, was developed in 1994 by Peter Shor. It was the first demonstration of a significant quantum speedup for a practical application, and it's applied to factoring integers in polynomial time. This provides an exponential speedup as compared to the best classical techniques with respect to time. At a high level, we can view Shor's as a way to improve the guess and check procedure for prime factorization. It contains both classical and quantum subroutines. And what it helps us to do is transform a bad guess of a factor of a large number into a better guess. So a bad guess G might share a factor with a target number n, that's our very large integer we're trying to factor. We want to increase the probability that G will share a factor with that large number n. Let's talk about some fundamental mathematics that we need to understand Shor's algorithm. To decrypt data, first, we need to know the prime factors of our target number n. So for n equal to g times h, we want to determine some g. The guess that we have for g doesn't need to be a direct factor of n. It can also share factors. That's because we can have the case where n is equal to a times b and g is equal to a times c. So therefore we have a accessible to us, which is a factor of n. For example, we can have 9 equal to 3 times 3 and 15 equal to 3 times 5. They both share a factor of 3, even though 9 is not a direct factor of 15. The largest value that divides two numbers with no remainder is called the greatest common factor. We'll call this the GCF. Euclid's algorithm can help us to determine a greatest common factor for two values. When we use it, it helps us determine if these two values share a factor. The procedure is as follows. We determine the largest of two input values and replace the larger number with the difference between the larger and the smaller. We repeat until one of the values becomes 0 or the two arguments are equal. At that point, the greatest common factor is known. Euclid's algorithm is incredibly useful and it's extremely efficient to implement classically. Let's do an example. What is the greatest common factor of 42 and 105? Well, we first determine the larger of the two, so that would be 105, and subtract the smaller from the larger. That transforms 42 and 105 to 42 and 63. We repeat the procedure until our numbers get smaller and smaller. At this point, when we have 0 and 21, we stop. We know that our greatest common factor of 42 and 105 is 21. Let's do another example. What is the greatest common factor of 6 and 35? First, we determine the largest number out of 6 and 35, and we subtract the smaller. So 35 minus 6 gives us 29. 29 minus 6 gives us 23. 23 minus 6 gives us 17. 17 minus 6 gives us 11. We continue this routine until we reach two equal values. The greatest common factor of 6 and 35 is 1. What does that mean? Since 6 and 35 share no other factor besides 1, that means that the two values are co-prime. This doesn't necessarily mean that the values are prime themselves. For example, a factor of 6 is 3 and a factor of 35 is 5. Guessing a direct factor of n is not necessary when we're trying to factor n itself. We just saw with Euclid's algorithm that we just have to find something that shares a factor with n and we're good to go. It'll still enable us to decrypt our secret messages. What we can do is we can apply Euclid's algorithm and check if our guess g shares a factor with n. If the greatest common factor of g and n is not equal to 1, in other words, they're not co-prime, we found a factor of n and we are done. We can use g and n divided by g to decrypt our message, because n divided by g will give us our factor of n. If our greatest common factor of g and n is equal to 1, we have found co-prime values. This is more likely, unfortunately. If we find co-primes, we need to do more processing in order to improve our guess for g. Let's introduce some more complex mathematics that will help us find a better guess for g. If two values do not share factors, so in this example, we'll look at x and y, they'll be co-primes and their greatest common factor is equal to 1. So we can take our co-primes x and y and relate them in such a way that we can take x, multiply it by itself many times, or in other words, raise it to some exponent p, and that'll be equivalent to m, some constant, times y plus 1. Here, p and m are both integers. Let's try this. So for our example that we previously worked, where the greatest common factor of 6 and 35 were equal to 1, we can take 6, raise it to the 2, and that's equal to 36. It's also equal to 1 times 35 plus 1. So using this relation we just described, we found that p can be equal to 2 and m can be equal to 1 in order to relate the co-prime values of x and y. This technique works for any set of co-primes. Using that earlier logic we just described, we can improve our guess of g in order to find a factor of n. So here we have g raised to the p is equal to m times n plus 1. Let's move that 1 over to the other side of the equal sign, and we're able to expand the left side of our equation in order to define g raised to the p over 2 plus 1 times g to the p over 2 minus 1 is equal to m times n. We can check with FOILing to see that both of these expressions are equivalent that are on the left of the equal sign. These terms produce improved guesses for factors of n because of Euclid's algorithm. Remember, we don't necessarily need to find a direct factor of n, we just need to find something that shares a factor. So let's improve our guess for g using the term we just defined, g raised to the p over 2 plus or minus 1. In our previous example, when we looked at n equal to 35 and g equal to 6, we saw that they did not share any factors. They were co-prime because the greatest common factor with Euclid's algorithm was equal to 1. For p equal to 6, we have 6 raised to the 6 divided by 2 plus 1 equal to 217. And then we have 6 raised to the 6 divided by 2 minus 1 equal to 215. Neither of these are factors of 35, but luckily we have Euclid's algorithm. The greatest common factor of 217 and 35 is 7, and the greatest common factor of 215 and 35 is 5. With these factors, we can break the encryption associated with n equal to 35. Although this is a trivial example, and in reality, our encryption would use much larger integers, this just goes to show the effectiveness of these techniques that are included in Shor's algorithm. So one may ask, where's the quantum in all of this? There's still the challenge of finding the right exponent p for g raised to the p divided by 2 plus or minus 1 that is equal to some constant m times our integer of interest n. And we need that value of p to improve our guess g. Not every p will work. We have a couple of constraints we need to consider. For example, we don't want a p-value that will produce a multiple of n. We only want factors. Additionally, odd values produce numbers with fractions, so we want to avoid those as well. As n gets larger, our search space for p increases dramatically. So testing many values of p would take a long time classically. Think once again about that guess and check technique we would have to implement. Lucky for us, quantum computers implement superposition and have interference between signals. So superimposed possible answers combined with interference will allow us to find the correct answer for p within a single computation. Here we have an example implementation using Qiskit for the quantum circuit part of Shor's algorithm, where g is equal to 7 and n is equal to 15. You can find this example within the Qiskit textbook. Just look for Shor's algorithm. To summarize, Shor's algorithm starts with making some guess g and checking if there's common factors with g and n using Euclid's algorithm. It's highly unlikely that g and n will share a factor. Because of this, we want to find some value p that improves our guess, and this involves a complex quantum calculation. With our improved guess, we will check the greatest common factor with n once again. If it's not equal to 1, a factor of n has been found. Success! Unfortunately, if our greatest common factor with our new improved guess and n is equal to 1, we have found two coprimes and we'll have to try again. We'll want to save that original guess though, just so we don't reuse it. Every time we repeat Shor's algorithm, the probability of failure decreases. Eventually, we will find a factor of n, and this is found in polynomial time of log m, where m is the size of our integer n.